So basically where we ended off last time is talking about this graph. So I went in and filled in a couple things because I didn't want to take up too much time from today because I know Dr. West has been moving a little quickly. So what I do want to go over with you guys is a brief intro to all the different aspects of NMR. So what are the 4 aspects that we covered last time? If anyone remembers. Something I mentioned yesterday is I really, really, really love participation. And so if you guys don't know an answer, that's completely fine. But sometimes when I ask a question, I'll literally just do an awkward dance until people answer. And you don't want to see me do an awkward dance. Okay, so someone asked a great question. They said, was there SI yesterday? So yes, my SI sessions are Monday, Tuesday, and Thursday. I was planning on sending you guys a little flyer that the class office makes so you guys know all my session times. But for some reason they hadn't made mine yet, so I will be sending that to you today. As I said, the session on Monday is at 3 p.m. Today is obviously 11:30, and then on Thursday it's also at 11:30. And then if you missed it again, it'll be in the email that I send out to you guys today. Oh, yes. Also, I blanked it out here. It says these times on the handout. That was completely my bad. I uploaded last semester without changing it, so I will be re-uploading this today with the correct times. That's completely my bad. I do apologize. Okay, cool. Now that we got that cleared up, some people answered there's integration, multiplicity, splitting, and chemical shift. And if anyone needs a quick refresher on that, I will show you guys what we filled in yesterday in SI. So the number of signals is just telling us the number of different peaks that we'll see on the NMR. The multiplicity and splitting tells us about the number of neighbors. We'll do a lot of practice on that because that's what tends to be the hardest for people. Chemical shift is just where something is on the spectrum, and that'll tell us if it's shielded or deshielded. And then integration is just going to tell us how many hydrogens or carbons we have per signal. So we're going to talk about all these things in more detail. But do you guys have any questions on the basics before we get into it? If not, I'll give you like one more second and then we can scroll by. Also, I know typing takes a while if you have a question. So just because I've moved on doesn't mean you can't ask your question anymore. Ask your question at any point and I will get to it whenever I see it. Also, if you don't want to type out a question, I have absolutely no problems with you unmuting and like saying it or saying your answer to a question. Again, I love participation. So however you would like to participate is cool with me. All right. So let's go back over here. So we drew this guy propanol, and we determined that there are going to be 1, 2, 3, 4 signals. And if you guys remember, I gave you this little analogy yesterday when we talked about upfield, downfield, shielded, deshielded. And so the more electron density something has, the more shielded it is, and the closer it is to 0. On the other hand, the less electron density means the less shielded, means the more to the left-hand side and a higher number. So when we talk about a molecule like propanol, the hydrogens that are closest to the oxygen are going to be the most deshielded because this oxygen is super, super electronegative. So it's stealing all the electrons for itself, right? So between HA and HB, which one do you think will be the most de-shielded? HB, awesome. I totally agree. And that's because both of them are directly at, that's because both of them are in the heteroatom region, but HB is directly attached to the oxygen, whereas HA is attached to a carbon next to an oxygen. So, guys, it did a great job. If we scroll back up here, we can see that as you get further and further from the oxygen, you're going to become more and more shielded. The next thing I wanted to show you guys is splitting. So I did the splitting here for you guys to see. Again, we're going to do a bajillion examples, but I wanted to point out, first of all, the heteroatom rule is something we covered yesterday, and if you weren't here, I'll reiterate. It basically states that you cannot split through a heteroatom. And a heteroatom is anything that's not a hydrogen or a carbon, essentially. So this hydrogen is 1, 2, 3 bond lengths away from the other hydrogen, but there's an oxygen in the way, so we cannot split. So that has to be 0 plus 1, which will give us a singlet. If you are in Orgo Lab, sometimes it does go through the oxygen, but your TA will tell you that. So for the purposes of lecture, it's never going to go through. That might not be true in lab. All these other guys are going to be higher than a singlet because they're all going to have neighbors. So for example, these blue hydrogens will have 1, 2, 3 bond lengths. So both of these purple hydrogens count as neighbors. We do 2 plus 1 and get 3. So it is a triplet. And someone asked a great question. The heteroatom is what? So basically a heteroatom is anything that's not a carbon or a hydrogen. So for example, a heteroatom can be an oxygen, a nitrogen, a sulfur, a fluorine, anything besides C and H. Any questions? So yes, here, let me scroll up so you guys can actually see it because I did write it down here. So the 3 rules of multiplicity and splitting are basically you have to be within 3 bond lengths, you use n plus 1 to count the number of neighbors, and we have something called the heteroatom rule. So a heteroatom is anything besides a carbon and a nitrogen, or anything besides a carbon and a hydrogen, excuse me. So basically it can be anything like an oxygen, a nitrogen, a fluorine, a sulfur, etc. So if you have one of these things in your molecule, you cannot count that as being one of the 3 bond lengths. So as an example, I will show you. Let's say we have this again, and I have this hydrogen right here. If we try to count 1, 2, 3 bond lengths, according to only that rule, this should work. But since we have this heteroatom here, it cannot go through it, so that cannot count as a neighbor. Therefore, this hydrogen is all alone. It's basically on its own island. It has no neighbors whatsoever. It's a singlet. Does that make more sense? Yes, no, maybe so. Okay, cool. I'm getting some yeses, so that's good. Alrighty. The last thing I wanted to show you guys on here before we move on is how I drew each of these peaks. So when we have a singlet, it's going to be one big peak. If we have a triplet, triplet is 3, so we're going to have 3 of these peaks. The sextet is 6, so so it's going to have 6 of these peaks, so on and so forth. Dr. West mentions this in lecture, so I will mention it here. You can't really tell from my drawing because it's not super wonderful, but these peaks are going to be like symmetrical. So this and this will be the same height, and the one in the middle will be taller. Same here, these two will be the same height, these two will be the same height, and these two in the middle will be the same height. You guys will see
Liz, I have
why.
a question.
Yes, go for it.
When the peaks are all jumbled up, how can you tell? Like sometimes it's hard to count, or would it always be clear in like the lecture to count them?
So, in lecture, he will make it as clear as possible. In lab, it's always going to be a disgusting mess. So it's hard to count, but I do have an example here for you guys. So if you have something like this is a question he has in his practice problems. As you can see, they are pretty jumbled, right? Like you would have to zoom in super close, and even then, like it's super ugly, right? So when that is the case, you are kind of just expected to look at other parts of the table. So what I mean is like clearly this one is a singlet right here because it's just one big peak. We can essentially just think of this as being a multiplet for now. And then we know this is a singlet. And this kind of looks like a triplet, but we're not sure, right? Because it's really disgusting. From then on, we can kind of use all the other information here to figure out what the splitting should be, or it's not important. I know this sounds like a lot because we haven't gone over everything yet, but all of that to say, if it's super important for you to know what the splitting is, it will be clear. If it's an example like this where it's really gross and you can't see it, odds are there's other information that can help you answer the question. And someone asked a great question, which was, what is a multiplet? So essentially, scientists are lazy. And so after you get like a 5 for our multiplicity, the numbers are like septet, heptet, octet. That's ugly, right? So instead, we're just going to call it a multiplet. And this rule is right up here. So if you guys want to write it down, basically anything that has 5 or more neighbors is going to be called a multiplet just for simplicity. So in this case, the sextet can also be referred to as a multiplet. Cool. All right. Awesome. Okay, so someone asked if I can go over why propanol has 4 signals. Yes, absolutely, and that's a good segue into this next, or I guess, so this was kind of a big summary that I wanted to use to show you guys just the different aspects before we actually get into each section. So now we're actually going to dive into counting signals, and I'm going to delete that example because that's one I did yesterday. But before we do these, I will redraw propanol and we can talk about it. Okay. So 1, 2, 3. This is our propanol. So let's just go left to right. We have 1, 2, 3 hydrogens here. And the first thing we're always going to do before I draw in the rest of the hydrogens is if we're counting signals, you want to always look at symmetry first. So is there any kind of symmetry in this molecule at all? No. Okay, cool. So that's one thing crossed off the list. We don't have to worry about it. So here we have a CH3, a CH2, and a CH2. Are any of these carbons the same, or are they all unique? Yes, each of these are going to be completely unique. So what that means is each of these hydrogen signals, or excuse me, each of these sets of hydrogens will have their own signal. So all of these guys will be signal number 1. All of these guys will be signal number 2. All of these guys will be signal number 3. And then never forget the one that's on the oxygen, because that's how he tricks you. People always forget that one. This is number 4. And someone made a really great point. So yes, all of the ones that come from the same carbon in this case are going to be the same. We will talk about something called heterotopic signals, which is kind of what he covered today in class. I know that tends to be super, super confusing for people at first, so I will go over that today. But for now, all of these are just completely different from one another, so we don't have to think about an anthrotopic, diastereotopic, anything like that. So altogether, we have 4 hydrogen signals, and let's count our carbon signals. We have 1, 2, 3 unique carbons. So this would be our answer. Any questions? Okay, so someone asked, do we need to know the ratios for splitting? So do you mean like here how he has the like 1 to 2 to 2 to 3? If that is what you mean, that's not necessarily for splitting, that's more for, oh, okay, so I think what you're talking about is the tree diagram and those ratios. For now, don't worry about it. We will super briefly cover tree diagrams on Thursday, but for the most part, just know you will never have to reproduce a tree diagram. It's very confusing. The only thing that tree diagrams are basically useful for is understanding conceptually what splitting is. But if you completely no idea what it is and it hurts your brain and it makes you want to cry, pretend it doesn't exist for now. You're fine with that. Okay, you are very welcome. And all right, so someone said, it is organic 2 just a continuation of organic 1, like the same book and everything? Yes. Dr. West doesn't really go by the book, but that is correct. Okay, so we're going to do a couple of these examples, and then we're going to talk about heterotopic versus homotopic signals. So the first one we're going to do is this guy that I just did a star on. So first thing is first, do we have any symmetry? And while you guys tell me that, someone asked, is there like a chart that tells us the NMR regions? Yes, we will get to that. I'll show you it either the end of today or the start of Thursday. But you can also find one in the book and in his PowerPoint. All right, so as you guys said, yes, we do have symmetry, and it's basically going to go right here. So let's count the hydrogen signals first, and then we can go down to the carbon. So having symmetry basically just tells us that everything on this side is exactly the same as everything on this side. So if we start with these methyls, we know that the methyls are exactly the same. Therefore, all of these hydrogens will be exactly the same. and they are all part of one signal. So all the purple hydrogens are just one signal. And then we go down to the next carbon right here. It has one hydrogen. It would be so cool if this would work. There we go. And we know that this hydrogen is not symmetrical to anything. It's all by itself, so it is its own signal. Down here, does this carbon have any hydrogens we need to draw in? No, exactly. A lot of people will draw one there and get tricked, but remember this is double bonded, so it has all of its bonds already. Moving down, we have this guy. So it has one hydrogen, and it is going to be exactly the same as this hydrogen on the other side. Moving down one, we have this hydrogen, and it is going to be exactly the same as this hydrogen. And last but not least, we have this guy. It is not symmetrical to anything at all, so it is going to be by itself. So altogether, we have 1, 2, 3, 4, 5 hydrogen signals. Also, before I move on, is this purple color and this pink color different enough for you guys to see the difference, or should I change the color in the future? It's good? All right. If anyone has any trouble with it at any point, let me know. Okay. So now let's do our carbon signals. First, we mentioned that these two are exactly the same. So that's number 1. And then we have number 2. And then this next carbon down, is that going to count as a carbon signal? What do we think? Yes, exactly. A lot of students will get tripped up and think that because there was no hydrogen, the carbon doesn't count. But remember, carbon signals and hydrogen signals are completely different things. All right, so next up, these two carbons are going to be exactly the same. These two carbons will be exactly the same. And this one will be different. So how many unique carbon signals do we have?
6.
6. Awesome. I agree. Yay. Any questions at all about these ones so wow, okay, cool. About this one so far?
Can you hear me?
Yes, I can.
Okay, so I just wanted to know, I see that when there is the same hydrogen signals, that means that you would have on either side the same carbon signals. Is that usually the case? Does that make sense what I asked or no?
Yes, so I'm just going to reiterate kind of to make sure I understood you correctly, but you're basically saying here when you have the two symmetrical hydrogen signals, does that always translate to having symmetrical carbon signals?
Yes, yes.
Okay, so yes, the reason these are the same is because of symmetry. So if we have a line of symmetry here, everything on this side will be the same as everything on this side. So carbon and hydrogen. But something you need to keep in mind is we have something called heterotopic signals, which something under that category is diastereotopic. So in that case, sometimes things that look the same can actually be different, but that is only going to be for hydrogens. So sometimes hydrogens can look the same, but they won't be. That is not going to be true for carbons. We'll talk about that in a second because I know it can be super confusing, but I don't want you guys to always think, oh, if the carbons are symmetrical, the hydrogens will always be symmetrical. Sort of, kind of, does that make sense?
Yeah, thank you.
Okay, you're very welcome. And someone asked, this is being recorded, right? Yes, it is. All right, so now that we've done one example, I want you guys to take a minute and work on these two, which I will indicate here. And then once you guys have taken a minute or two to work on that, we are going to go over it together.
Another question, not related to the lecture, but
Yeah.
you mentioned yesterday that everything was going to be uploaded like on WebEx, and I went back to like look at the the recording from yesterday, and it just wasn't there.
Mm-hmm. Okay,
So do
so
you have to
sometimes,
upload?
sorry, go ahead, what was that?
And you said that sometimes you post them on YouTube. I don't know if like we could get the link to that too.
Yes, here, let me send that to you right now, actually. Sometimes my WebEx just doesn't work. Like, for some reason, the other semester, like, it never uploaded anything. And if it did upload something, it was really difficult to watch. It didn't have video, or sometimes it didn't have video, which is really inconvenient. So it's not uploading on its own. There's nothing I can do about it, I don't think. I'll email my supervisor just in case, so you guys have both options. But yeah, I will send you the YouTube link because that tends to be so much easier to access. I am just trying to open it up right now because I didn't pre-save the link for you guys, which I totally should have done. Okay, so I am sending the link in the chat right now, and I will also send it in the email that I will send you guys later today. If only this would work, that would be so awesome. Okay, cool. Please let me know that you guys can see the link because it's being strange for some reason. All right, so if you guys do look at the link, you'll see that there's a bunch of stuff already posted. So I will use this as a good time to pause really quick what we're doing and kind of, if this would at all work. Thank you. Here, let me share my screen. You are very, very welcome. I find the YouTube thing to be so much more helpful than WebEx sometimes. Okay. You guys can see my screen now. Yes?
Yes.
Yes, okay, sweet. So when you go onto the YouTube, there's a bunch of stuff already uploaded, and this is everything from last semester that I did. So you guys are able to still view those. I'm not gonna like private them or anything because I think they can be super useful. And so anything that just has a name like this with no date or anything saying SI or tutoring, these are just little sample concept videos I made for you guys. So everything up through chapter 14 has these concept videos. The rest of them I haven't uploaded yet, but we'll get to that eventually. So everything like intro to NMR, which is stuff we did today or last time, versus 2D NMR versus counting signals. You can click on these videos and it's basically me covering the whole concept beginning to end, and like writing everything out and filling in the handout. I think these are super useful because it's like just done straight through and there's no like weird noises or distractions and whatnot. The only downside is it's not like live, so no one was there, and so there's no questions and answers, which if you get distracted by questions, I guess this is helpful, but if you like hearing other people's questions, that's something missing from here. All of these sessions that say like a date and it says SI versus tutoring, those are actual SI and tutoring sessions that were recorded last semester and uploaded. Unfortunately, I never went through and put like what topic is being covered what day. So you kind of have to just like search around. But again, some people find it super helpful to look over those. I also have exam reviews from last semester, which I think are also super helpful. I will be holding exam reviews this semester, but if you ever wanted to look over something or get a quick review, I think that's super helpful. The only thing I don't suggest doing is watching this like as your only source of studying, because I know that's tempting, because I don't cover everything possible in these exam reviews. So for sure, don't use that as your only study material. Other than that, I also have practice problem sets. So me and Katrina, who was my SI leader buddy last semester, she's a tutor now. She's super, super wonderful. Love her. We did these for you guys where we're basically just answering practice problem sets. I recommend you watch this after you do them yourself, because it's the best way to study in this class is to do these practice problems. So these can be super helpful. I recommend watching them after you do the problems on your own. And yes, that is it. If you don't know what Up Owl Night is, that's basically just the final exam review. And if you go to playlist here, I'm not going to show you all of the private ones, I guess. I don't know why it's whatever. That's basically just where I put everything into categories. So everything for chapter 9 is in one playlist, everything for chapter 11 is in one playlist, so on and so forth. And I will make a playlist specifically for this semester's tutoring sessions and this semester's SI sessions, so that you guys aren't confused about what's what. All right, that was a lot. It was a mouthful. Do you guys have any questions, comments, or concerns about that? And yes, I will. Oh, thank you. Someone said it's very cute. So someone also asked, will I be uploading yesterday's and today's? Yes, I for sure will be. I will do that today. Sometimes it takes a little bit for me to have the recordings after the semester, the session, excuse me, is done. So as soon as it's available, I will upload them. It might take a couple hours, but it will be up by the end of the day. So yes, exam 1 is just going to be chapter 9 and 11, as far as I know. I will be meeting with Dr. West at the end of this week or the beginning of next week, just to kind of know what what topics from each chapter is going to be on there. But yeah, no chapter 10. We don't do chapter 10 in this class, thankfully, because radicals are gross. We don't stand radicals. All right. So if you guys have any more questions about this YouTube thing, let me know. If not, I'm going to close it so you can go back to sharing the SI handout. Someone asked, is it 11 and 12 or just 11? So last time it was just 11, but again, I'm going to meet with him just to double check, because sometimes he groups 11 and 12 together. So I will let you guys know. Oh, thanks so much, guys. I'm obsessed with like making things aesthetically pleasing, so I appreciate the feedback. Okay, I'm going to stop sharing here, and I'm going to start sharing the handout again. Alrighty. Good? Can you guys see the handout? Cool. All right, so I will give you guys like a minute or two to do these two on your own. Think about how many carbon and hydrogen signals you would see, and then we will cover it together. So again, I'll give you like a minute or two and I'll stop talking, but feel free to ask any questions and I will answer them. Also, while you guys are doing that, I sent the attendance link one more time. Pretty please, if you have a chance and you haven't filled it out already, please do so. I will also send it at the end of the session. Okay, I think it has been 2 minutes, but I have no concept of time, so I apologize if it's been more than that or less than that. Is everyone ready to go over it, or would you like some more time? Oh my gosh, wait, you guys can send thumbs up? That's so... Wow, I did not know that. Have I just been super oblivious this whole time? Wow, wow, wow. I love it. Okay, cool. Everyone's sending emojis now. I'm pumped. Okay. Just all the time. Send me those for everything. Cool. Every time I make a joke, I expect to see like 100 of those laughing emojis popping up. Cool. Perfect. Love it. Okay. So let's go over these. So for this first one, do we have any symmetry?
No, symmetry.
Yes. Okay, cool.
Never.
So, sorry. I love the confidence and I love that you answered though. But we do have symmetry right here along this plane. So if we folded it right here, this would be on top of this. So we are going to have like symmetry this way. You guys can't really see my hands, but whatever. Any questions about that? Okay. So if we have symmetry, that means everything on this side of the line will be exactly the same as this side of the line. So this methyl and this methyl, are they going to be the same or are they going to be different? The same. Awesome. So all of these hydrogens are exactly the same. So what is the integration of the purple signal? Ooh, 6. Awesome. So basically all that means is how many hydrogens are there in the purple signal. So there are 6. So the integration is 6. And someone asked, what is that? Basically, integration is just how many hydrogens there are per signal. So in this case, there are 3 plus 3. And yes, so basically how many total purple hydrogens? Yep. So we move 1 down and we have 1 red hydrogen. And is there anything symmetrical to the red hydrogen? No.
No, it's fine. So
Awesome. Perfect. So the oops, I don't know why I did a plus sign. The integration is just going to be 1. So now this 1 blue hydrogen and the one opposite to it are going to be exactly the same. So what's the integration going to be? 2. Awesome. And this last one over here, all by itself, is going to have an integration of 1. So how many total hydrogen signals do we have? 4. Perfect. So before we cover carbon, does anyone want to take a gander and tell me what they got for how many carbon signals we have?
I got 5.
5. Awesome. I agree. So we have 1 here. We have 2. 3, 4, and 5. Yay. Okay, so someone asked, why aren't the red and green symmetrical? So since the line is going here, everything that's on this side of the line overlaps with this side. So purple overlaps with purple, blue overlaps with blue. However, since these two methyls are like right here, this point and this point will not overlap with each other, and they have nothing else to overlap with because they are on the line of symmetry. So that basically just means that they are going to be completely by themselves with nothing to be symmetrical to them. Good? Okay. So this next one, I want you guys to tell me before I do anything, how many hydrogen and how many carbon signals you guys think there are. Oh, okay. So you guys said 3 hydrogen and 4 carbon. And let's go through it real quick. So we have our line of symmetry again. So first we have the 2 methyls. Bam. Awesome. Next carbon down, this doesn't have any hydrogens on it, so no H signal. And someone actually pointed this out. The integration will be 6. Awesome. So I will write it down. Next up, we have this hydrogen, which will be the same as this hydrogen. And the integration will be 2. Perfect. And then one more down, we have these 2. Ta-da! And this is also 2. So you guys were absolutely right. There are 3 hydrogen signals. And when we count carbon, we have 1, 2, 3, 4. So we have 4 carbon signals. You guys did wonderful. Yay. All right. So please let me know if you have any possible questions at all whatsoever about counting signals. Something I said yesterday, but I'll repeat. There's no such thing as a stupid question. I will never be upset or annoyed by you guys asking questions. So I would 100% rather you ask me a million questions and understand it and do well on the exam than to just sit there and be like, oh, I'm dumb. I don't want to ask the question. No, I asked about 2 bajillion questions a day when I took the class. So, okay, so someone asked, is drawing it out the best way to answer these types of questions on the exam? So, honestly, exam 1 is always tight on time because NMR takes a lot of time to do. So I want you guys to do as many practice problems as possible so that questions like this, for the most part, you can look at it and you don't have to draw out every single hydrogen to be able to find it. But in order to do that, you have to do lots and lots of problems and draw them out on all the problems. So my short answer is draw it out as many times as you can before the exam so you don't have to necessarily draw every single one out on the test. So someone asked a great question. It was, so if the planar line crosses a hydrogen, they're different and not symmetrical. So in these cases, yes, but I will give you guys another example here. So let's pretend we have, that's an ugly benzene ring. Okay. So let's say we have this guy, right? We have a line of symmetry here. And we also have a line of symmetry here. So in this, I'll call this line A, and I'll call this line B. We have a hydrogen right here and a hydrogen right here. And this line of symmetry goes through those two, right? However, they are still the same as one another because now the substituents are going to be on another line of symmetry that makes them the same. I know that's a really weird way to word it, but does it sort of kind of make sense? Yes, exactly. So in this case, it's kind of going to be cut into fourths instead of into halves. You're absolutely right. Same thing here. So we have a line of symmetry here, and we have another line of symmetry here. So each of these quarters is going to be the same. Cool. You are so very welcome. Okay, so it is 12:26, and I believe I was supposed to be done at 12:20. So here, let me send you the attendance link one more time. If you didn't do it, please do the thing. Next time we will be talking about homotopic, heterotopic, all that kind of jazz, and we will be doing chemical shift. As I mentioned, I will be sending you guys an email today with all the possible information you guys could ever want. If you have any questions about that, please feel free to email me or send me a message in Canvas, whatever you would like to do. But yeah, that is all I have for you today. Yes, and for anyone who wants to take a screenshot or anything, I will be going back up and scrolling out, zooming out so you guys can see it. So here, let me turn it this way. That might be easier for you guys. If it just looks a lot worse, let me know and I'll change it back. Oh, and people are saying thank you and that things are finally clicking and things like that. That makes me so happy to hear. You guys have no idea. Have a wonderful day. I will also scroll up to the first page if you guys need it. Just let me know when you're done with this one. And again, ignore the time. I will fix it.
Did you say there was a link for the attendance?
Yes, here, let me send it to you. If you click on it, it'll just ask you like for your name and your Z number.
Okay, thank you.
You're so welcome. And page 3. Yes, so this is not something, this is something I did in tutoring, so don't worry about it if you weren't in tutoring. But yeah, I will show it to you just in case you want it.
When you do tutoring, is it like an appointment with one student that you did it with, or was it with a group?
It is with a group, so tutoring online versus tutoring in person is a little bit different now. Tutoring in person, I have 2 people per session, so it's a lot smaller of a group. Online, it's going to be 10 people, and you are going to go to the website fau.edu/tutoring, and you can click on my name, and it'll show you all my hours, and you can sign up for a specific hour. And as I said, if you do the in-person one, you have to actually come to campus, and it'll be just you and one other individual. And then online, it can be between 5 to 10 people. Does that sort of kind of answer your question? Okay, so the in-person tutoring is going to be located in the SLC, which is kind of a new building. It is next to the football stadium. You know the new like sports center thing they made? It's inside of there. So once you enter, it'll be super easy to find. And if you need any directions or any help getting there, you can always send me an email or call the class office, and they will give you better instructions. Okay, so I'm going to Yes, what's up?
How do you make the appointment with you again?
Here, I
I'm
will show
I'm
you.
on the website. Okay.
Okay, here. So let me stop sharing this screen. All right. So